The yellow truck is moving at a steady speed, and the green truck coming from behind has a higher speed. Brakes are applied, and the green truck slows down. In the case shown, the rear end collision has been just avoided. The velocity of the two trucks became equal when the distance between them became zero. You can watch that here. When the velocity of the two trucks is equal, they're just touching each other. So the truck in the front continues to travel at a constant speed. The truck at the back has applied brakes and has slowed down, and just as they made contact, the velocities have become equal, and so collision has been just avoided. On the other hand, distances were a little lower. This is what would have happened. The truck at the back has a higher speed because it couldn't slow down enough. So just as it makes contact with the rear of the front truck, its velocity is higher and there is a collision. On the other hand, the gap were larger, well, they won't make contact. In this animation, it is shown that the green truck stops. It doesn't have to. When the velocities have become equal, then it can travel at that constant speed and the gap would not change. Or even if they made just made contact, at that moment, if the velocities are equal, they can continue to travel in the same direction, and that would also be a way of avoiding collision. Watch again the case where the collision was just avoided. This case, collision was just avoided, and you see that when the velocities are equal, they've just made contact. You can see the green vector here and the yellow vector of equal length. Also from the graphs, the green line here is the motion with constant velocity of the truck at the back. It's got initial velocity of 8 meters per second. And this yellow line is for the motion of the yellow truck, and that's got a constant velocity of 4 meters per second. So at the moment when they made contact, they both have equal velocities of 4 meters per second. Collision has been just avoided. This is a position time graph. It's a line inclined to the x-axis, this for the yellow line. The green line is a portion where the velocity was constant. Then as the truck slows down, that red line is a curve. The tangent to the red line at the top is parallel to that yellow line. So we want to watch that again, so let's do that. Collision has been just avoided. Two trucks are moving on a narrow road in the same direction. The truck ahead has a speed v1. The truck behind has a speed v2, which is greater than v1. The driver of the truck at the back notices the truck in front of him when it is d ahead of him, and he applies brakes to avoid collision. Well, how does he avoid a rear end collision? That's our interest. Now, if two trucks are moving in opposite directions, they both have to come to a stop to avoid collision. You can easily imagine if one of them stops, the other is still moving. When the distance between them becomes zero, there will be a collision. So both of them must come to a stop before the distance between them becomes, or just as the distance becomes equal to zero. What about in this case? The driver of the truck ahead doesn't know that there is a truck behind him, so this will continue to travel at v1, whereas the truck at the back slows down. It is enough if it slows down to a speed v1 just as it covers that distance d. So speed of the truck at the back has to reduce from v2 to v1 just as that covers that extra distance. In this time, this truck would have moved ahead and so by the time this d plus that extra distance is covered, the speed of this must reduce from v2 to v1. We would like to find a relation between various parameters, well, for the collision to be avoided, just avoided, say. Now if the position of the first truck is, say, A and the position of the second truck is B, and well, just as the speed of the truck at the back reduces to v1, this happens at, say, C, we can write some equations here. We are seeing two trucks moving here. The truck at the front moves with a steady speed v1. The truck at the back is moving at, well, v2, higher speed v2. So brakes are now applied. The distance is d. That's brakes are applied when the distance, well, between the two trucks is d. So the truck at the front has moved a distance at a steady speed. So if this happens in time t, this will be v1t. This is an accelerated motion. The truck is slowing down. Let's write the third equation of motion for the truck at the back. The truck at the front has a steady motion, so there's nothing much to do there. So you have v2 squared should reduce to v1, right? v2 should reduce to v1. So v1 squared is the final speed. That's equal to v2 squared plus 2a into, and this is d plus ac. D plus AC, A into, this is D plus AC. AC is traveled at a speed of v1, so that's v1 into time. That is, time is what the speed of the truck at the back is reduced from v1 to v2. So v2 is v2 to v1, so v1 minus v2 by A. That's the time. So this is v1 into t for the distance AC traveled by, moved by the truck at the front. So this is the equation you can write, and a little manipulation here will give us a relation between v1 squared is v2 squared plus 2ad, the 1a gets cancelled, plus 2 into v1 minus v2, right? This a has got cancelled, 2 into v1 minus v2. So this is v1 squared, so this is 2 into, there is a v1 here, right? There is a v1 here, sorry. 2 into v1 into v1 minus v2. This a has got cancelled. So this is 2v1 squared. Take it to this side. That will be minus 2v1 squared. So this is minus v1 squared. This is minus 2v1 v2. That becomes plus 2v1 v2. This minus v2 squared on the other side. That is 2ad. So this is, if you observe the minus sign, this will become minus v1 minus v2 whole squared. That's equal to 2ad, or a is equal to v1 minus v2 whole squared by 2d. It has to be negative. The truck has to slow down and stop. So this is the condition. This is the minimum deceleration the brakes must produce in order that the rear end collision is avoided. This is a problem solved in the reference frame of the ground observer who sees both trucks moving. Let's switch our reference frame. So let's switch to the reference frame of the observer in the truck at the front and see how this works out. This is the reference frame of the truck at the front. So in this reference frame, the truck at the front is at rest and the truck B is moving at a speed of v2 minus v1. Right, that's v2 minus v1, and when it makes contact, the observer in the truck at the front says the speed is reduced to 0. Ground observer sees speed changing from v2 to v1. The observer in the truck at the front sees the speed changing from v2 minus v1 to 0. So it becomes pretty simple there. So final velocity is 0, 0 squared. We are writing the third equation of motion for the truck at the back as seen by the observer in the truck at the front. So this is speed of the truck at the back initially relative to the truck at the front. That is v2 minus v1 whole squared plus 2 into a. A is unknown to us. The distance covered by the truck at the back, if the truck A is imagined to be at rest, truck B has covered all the distance d. So in the reference frame of the truck at the front
The truck at the back has covered a distance d. So initial speed is v2 minus v1, final speed is 0, and the distance covered is d. And we've got the relation. What is a then? Minus v2 minus v1 whole squared by 2d. Simple. So, well, this you've been doing now and then. When two objects are moving, it may be best to switch to a reference frame of one of the objects, so you have simpler equations to write. This is what has happened here.